Bienvenidos al CESGA, el Centro de Supercomputación de Galicia. El CESGA está comprometido con la iniciativa do Campus do Mar, apoyando las iniciativas relacionadas con la simulación numérica y la clasificación y el análisis de los datos aplicados al mar. Dentro de este campo, está colaborando con diversas entidades y grupos de investigación en la ejecución eficiente de simulaciones numéricas, en la creación de entornos sencillos de trabajo para la comunidad investigadora o en la categorización, referenciación y visualización de datos relacionados con el mar. Dentro del ámbito de la aplicación de la simulación numérica, hoy tenemos el placer de tener con nosotros al doctor Marcel Curé, especialista en simulación oceanográfica y sus aplicaciones, que nos hablará sobre el papel de la simulación numérica en el desarrollo de la energía renovable proveniente del mar, especialmente la proveniente de las olas. El doctor Curé es director general de la empresa irlandesa Numerics Warehouse Limited, que ofrece servicios de modelado numérico y datos para el sector marino de energías. Él es ingeniero naval, además de doctor en oceanografía. Tras su doctorado, sus investigaciones se centraron en los mecanismos de transferencia de gases sobre la superficie oceánica que provocan la ruptura de las olas, participando además en diversos proyectos de validación de nuevos aparatos de medición oceanográfica. Como experto en simulación numérica oceanográfica, Curé ha creado modelos numéricos para el Instituto Irlandés de la Marina, para prospecciones petrolíferas marinas o modelos de olas para la emergente industria de la energía renovable marina en Irlanda, tema del que nos hablará hoy. Antes de darle paso, me gustaría recordarles que estamos en directo a través de la televisión del Campus del Mar, por lo cual, si alguno de los presentes quiere hacer alguna pregunta o comentario durante la charla, por favor que espere a que le pasemos el micrófono para que los televidentes, en este caso, puedan escuchar la pregunta. Si nos estáis escuchando en remoto, recordaros que tenemos también un chat abierto para que podáis hacer preguntas o comentarios que serán traducidos por uno de los presentes. Bueno, muchas gracias de nuevo a todos por venir. Doctor Curé, thanks for accepting our invitation. It's really a pleasure to have for us to meet you here in Santiago and have the opportunity to learn how to apply the numerical modeling to the new energy area of the sea. Thank you very much.
Thank you, Andres, and thank you for inviting me to Campus del Mar, and it's a pleasure to come back to Santiago. Lo siento que no puedo hablar español con ustedes y tendría que hacer más caso a los discos españoles que regalo mi mujer. La próxima vez será mejor. Thank you again. I now speak English. It's a pleasure to come here. What I'm going to talk to you about, I could have talked to you about some other aspects of modelling that I'm involved with, but I would like to talk to you today about the exciting possibilities of wave energy and its development for those who are interested in numerical modelling, and how perhaps in the future, in the next future years, there will be many opportunities for diverse applications in its implementation. So I'm going to talk to you about the industry in Ireland, what's happening now, and what we hope the way it will develop. So, when I started my company 2 years ago, I thought that the most important thing is to simply to map the resource of wave energy, and everything would flow from that, okay? In other words, you need to know where there's the most wave energy and how much electricity you might generate from the waves. So the first thing we did was to implement a series of nested models from the Atlantic scale. And on the left here you see the result of nested wave models down to 3 kilometer scale from the Atlantic, and which were run using the model SWAN for 10 years with data saved every 3 hours from those fields of typical wave parameters. And there you just see the amount of wave energy, the mean wave energy potential over those 10 years, average over those 10 years. And you see that probably the best wave resource in Europe is in the northwest of Ireland. So what we did was, for the whole coast of Europe, down to Galicia really, we have a series of small nested models, those green rectangles, where the data is stored, the spectral data is stored around the boundaries, and we can very quickly implement a multi-annual wave model for a specific locality, if you have good bathymetry, for detailed studies. And the kind of spectral data that is stored around those boundaries, you see just an animation there on the bottom to drive those models. The other thing we did was to look at the overall picture, the big picture if you like, of how wave energy might look in a mature scenario, say in 2050 for Ireland, and how it interacts with other types of renewable ocean energy from tidal turbines and from offshore wind. And the intention is to see if they are complementary, or if you are going to end up with very big spikes of energy to the electricity grid, which might cause problems because of the backup power you need to supply a constant energy level to the cities. And here we see just, I'll show you a simulation in a minute of if you store model data from a hydrodynamic model, we use ROMs, and from wave models, SWAN, and from a weather model, WRF, which I think some of you, or many of you will be familiar with those models. You store that data, and then you, if you have the ability to just insert individual wind turbines, tide turbines, and wave energy converters in localities with their key characteristics like their size, their efficiency. For the wave energy converters, we know, for one or two wave converters, we know a little bit about how they react to the wave conditions that they are presented with. So the software we have allows you just to insert different wave farms with those devices, and then you use the stored numerical model data to actually calculate how much electricity each of those produces and how the mix comes together. So there's a nominal, in this scenario, there's a nominal 15 gigawatts of capacity in offshore energy for Ireland, and but how much of that is realized at any moment? So the red bar to the left is the wind energy. The green bar is the wave energy, and then the bit you can't see on the right is the tide energy. And in the map you see the symbols depicting wave energy converters, the wave farms, if you like, the offshore wind farms, and the circles are tide turbine farms. And I'll just run the animation. Oh, I've done it again. I'm sorry. You can see the amount of energy that's produced here, and they occur at different times. So the total power output in the bottom right-hand corner, and you usually get a lot less than the capacity of the devices that are there. But wave energy is much more regular than the wind energy, which I think is an interesting conclusion in its own right. So even though wave energy converters are in their infancy still, there are no big wave farms anywhere, there's a tremendous potential for and use for wave energy in the renewable energy mixture. In fact, calculation in Ireland by the Marine Renewable Industries Association that Ireland could produce 9 billion euros of exports. Now that is many times the electricity requirement of Ireland, but the market potential there is to export that electricity to the UK. So that is the glittering prize. I wish I was using my computer. So, I missed this slide, I think. who are we? We are a small company based in the west of Ireland. We have very good links with the universities and public sector in Ireland and elsewhere. And it is our mission to find ways of using numerical modelling to assist the renewable energy industry. And we act as a technology partner. And importantly, we can act as an independent and impartial assessor of the prospects, because many of the wave energy companies have their own groups that are doing their numerical modelling, for instance, but people don't believe them because they're trying to sell their own particular devices, for instance. Our modelling, we use supercomputers, much as you do, and we try to tailor the products we produce for the engineering applications, and there's a big gap. People that run models, produce output, how do you use that data? Because in the utilities, in the engineering design companies, they often do not know how to use the vast volumes of data that are produced by our modern models. Right. So how do we develop wave energy in Ireland? Well, one of the very big problems is the electricity grid. The electricity grid is designed for very large units of power production from either nuclear or coal, gas, and you have very high voltage grid connections between those locations and the major cities. This is not at all what you need for offshore energy, renewable energy, where you need to have high voltage grid connections from quite remote locations. And it takes a long time and a lot of money to improve the grid. So it's very important to get it right and to plan ahead. Well, there's a study in Ireland to look at how to join up the grid and to connect it with Scotland, especially, with an offshore grid. If you can expand your grid to be larger than 1 Rossby radius, or the typical size of an atmospheric depression, then you have the possibility of smoothing out those bumps in the output of renewable energy. One concept that's being looked at, the so-called North Isles grid, this is a project being conducted by RPS Kirk McClure Morton, a private company in Ireland, is to have this offshore grid connection between Scotland and Ireland. In tandem with that, there are plans to improve the grid to the west of Ireland, especially to the northwest of Ireland, where you saw those the very large wave resource. I'll just go through just the development of the wave industry in Ireland quickly. It all started in 2006 in Galway Bay, where I live, where the Marine Institute established a small platform in the bay for testing of novel wave energy converters and quarter-scale wave energy devices, typically with a nominal power output of 250 kilowatts, perhaps. And the government also provided monitoring capabilities, some modelling that I was involved with, to look at the design issues and so on. Following on that, Ireland set its targets of 500 megawatts of ocean energy by 2020. Quite optimistic. Now, that seems quite optimistic in the current economic climate, with 40% of all our energy usage coming from renewables. And then the government established, through an Act of Parliament, Sustainable Energy Ireland's Ocean Energy Development Unit. So this is like a central authority in Ireland which coordinates all the research activities in the country and assists with the technology developers to use the mechanisms of the state to fast track the development of their novel converters. In parallel with that, there's a wave tank been established in Cork, in HMRC. The Marine Research Industries Association was formed 2009, which brings together all the different groups under one umbrella organisation to lobby government, and to talk to the media and so on. And then in 2010, the first site where full-scale wave energy converters can be tested was established in Belmullet. Now that is in the northwest corner of Ireland, where the biggest wave energy resource. And I'll show you some results of a study I've done there looking at the waves there. Airgrid, the state-owned grid company, outlines its plans to expand the grid. In 2011, a feed-in tariff, a price support for wave energy, offshore energy, was established at €220 per megawatt hour. That's necessary for to provide certainty in a very uncertain venture to develop wave energy. In 2011, the ESB, which is the state-owned electricity company, production company, announces Westwave, which is a project to actually develop the first wave farm. And I'll talk a bit about that and our involvement in that. For the last couple of years also, a number of things have been happening which are necessary. There's the Offshore Renewable Energy Development Plan, which is how Ireland would like to see wave energy develop. The Strategic Environmental Impact Assessment looks at impediments and problems in implementing the OREDP and foresees how the sector, the wave energy sector, tidal energy sector, might sit alongside established aquaculture, inshore fisheries, tourism, and so on. And now, as a white paper recommending certain areas, integrated development zones, where it'll be easy for wave energy companies to get the kind of planning consents that are required to streamline the consenting arrangements to put in wave farms. Because one of the big problems, the biggest problem we have, is that the public authorities in Ireland do not understand the issues involved in putting these large installations at sea. And so they kind of panic and do nothing, you know. The different groups and the different government departments don't talk to each other. And what's required is to make this happen faster, for everyone's sake, but to respect the ecological diversity and the marine environment. So the Sustainable Energy Authority of Ireland is the state body I told you about. It has developed a number of phases at the bottom there. The first is a development phase, which ended in 2007, centred around the Galway Bay quarter-scale test site I told you about. Pre-commercial, this is what we're doing now, really, with devices being tested. Well, I think we're behind. The first full-scale wave energy converters hasn't yet been put into Irish waters. Pre-commercial number 2, up to 2015, is to actually produce power from a small wave farm, maybe 5 megawatts. And then beyond 2016, we expect electricity companies to be able to make money and sell electricity from offshore energy, we hope. So the location, here's another, just a wave energy map. And I know that in Meteo Galicia, you've been doing your own wave energy studies. Pablo's here, and I've translated some of your Galician to understand what you did in your report. Use Google Translate. I did a similar exercise I'll talk about in a minute, but there you see Amets. That's the name of the full-scale wave energy site that's been established in Ireland. There we see just a nautical chart showing the proposed grid connection, offshore grid connection. That grid is now, should shortly be in place to an offshore location, the red rectangle to the left, for buoy-type devices, an inshore location for smaller buoy-type wave energy converters, and one that isn't shown but close to the shore, a location for wave devices that are meant to be on the shore, very close to the shore line. And there you see, just on the bottom left, you see a swath multi-beam bathymetry map of the site. And those little circles are just the mooring arrangements for that are envisaged. You can see that the location of the underground, the submarine cable, has been chosen to miss a lot of rocks. Because it's so rough, because there's so many waves, the nature of the seabed is quite rocky. It's rocky, sandy. This is something I'll talk to you a bit more about. It's one of the big technical problems is how the mooring arrangements and the anchoring arrangements for wave devices, and how to get the power back to land. If you have too much rock, then you can't bore through. You can't put a horizontal drilling. It's difficult to bury the cable, and you don't want it too rocky. It could damage the cable. So a study that we were awarded last year was to do the wave climate for AMETs, and I'll talk to you a bit about this now. That's been submitted now. It took us 6 months, and basically it's a 15-year wave climatology with model outputs stored every 3 hours, to produce a digital atlas, to group that data in terms of overall seasonal, annual fields, to output some data from stations, which are just locations in the sea where we think wave energy devices will be put, and including spectral data, directional spectral data, and then to produce a number of engineering type products from the data that we've been asked by the industry to, in the kind of the format that they expect that data to appear so that they can develop their devices. But also to develop a model that can be improved in the future, and I'll talk a bit about that as well. Oh, I showed you just in the previous slide, I won't go back, but there's it just showed the lighthouse there, Eagle Island Lighthouse, and you saw just how rough a location that it really is. And perhaps it's not the best place to develop a wave, to put your first wave devices in the roughest place in Europe, but this is what they've chosen to do. So on the left here you see, this is just the development of the bathymetry, the different surveys that led into that bathymetry. Some of it just research vessel tracks, some of it swath data, multi-beam data, some of it LiDAR data, gridded to make sure. You can see just how complicated the seabed is in this box, which is 30 kilometers by 20 kilometers. And then you'll be familiar with the downscaling methodology, which I've used here. To run a wave model, the most important thing is to get the wind right. If you're looking at in detail at a particular locality, then you can't just use the climatological winds that are like NCEP reanalysis or ERA 40 data, because it's just too coarse and the time resolution isn't good. So you need to run a weather model as well, and the weather model we run WRF, downscaled from Atlantic to Northwest Europe to Northwest Ireland to the locality of AMETs, down to 2 kilometers resolution. And then in tandem with that, you have the wave model, starting with WaveWatch 3 for the North Atlantic. I'm sorry about you can't see the coastline very well there, but the dark blue is the coast. We also include the effect of the sea ice around Newfoundland and its variability, and how it influences the fetch of the waves. The wave energy that arrives in Ireland often has travelled the whole ocean basin to arrive there. And the biggest waves we get are when you have the isobars aligned across the whole Atlantic and you have swell coming from Newfoundland all the way across to Ireland. So you have to include that in the model. WaveWatch 3 down to Swan, 3 kilometers resolution, Swan, 100 meters resolution, all with spectral data around the boundaries. For 15 years, model field stored every 3 hours. And again, you see the bathymetry for our study area, AMETs, and you see where the cable's going to lie, and you see those spots there are points chosen, stations chosen for detailed model output and some locations of some wave measuring devices we use for the validation of the model. And then just the overall result, you see the mean wave power over 15 years, confirming the location as the roughest place in Europe. And then just fields for winter and summer over the 15 years, you see the huge difference. You see the tremendous spatial variability of the wave power, which relates to the underlying rocky bathymetry of the region, and how important it is to choose the location carefully for where you put wave energy converters, what to expect. With the rocky outcrops, you're going to have a lot of wave refraction, and so you even over distances of a few hundred meters, you get a very big change in wave climate. The models, by the way, were all run on our supercomputer in Ireland called iCheck, which is a 3,000 core Intel-based, Westmere-based computer. And then just to show you the mean significant wave height. The mean is quite low, 3 or 4 meters. The peaks, this is the biggest values of wave height over the 15-year period, up to 16 meters, significant wave height. Just time series, over 15 years again, wave power for an inshore location, 20 meters depth, for an intermediate station in 70 meters depth. And, you know, in 2000 and the end of 2001, you see peak wave powers there in excess of 250 kilowatts per meter of wavefront. Tremendously violent conditions. Something that the industry is interested in is the variability in direction of the standard deviation of the direction of the waves. And the biggest variability comes in the summertime. In winter, the waves are much more unidirectional. This is what's called a power matrix, and it's one of the main outputs that the wave energy developers wanted from this study. And it just shows a table, if you like, showing the significant wave height against the peak wave period and the number of half-hour model outputs that correspond to those values. And then the contours are the theoretical energy transport for deep water waves. And you see that, and what they have, say Palamis, one of the main wave energy converters, they have a table that for each of those values they can calculate how much wave power is actually produced by their wave energy converter. So that's the kind of table I used in the first simulation I showed you to calculate the wave energy. Okay. Here we see just the exceedance of the power by month, by year, and you just see how tremendously variable the wave power is year to year. So on the bottom you have just the wave power, and on the percentage exceedance on the vertical axis. And here we have the where and what direction are the waves coming from. In shallow water, the waves are quite unidirectional from the west. As you go further offshore, unexpectedly we find that waves are coming from 2 main directions, from southwest and northwest. But it's much more variable. Why this is important? Well, some wave energy converters have to be put into the sea, and they don't easily adapt to the directions that the waves are coming from, especially the shoreline devices like Aquamarine's Oyster technology. So it's like a solar collector. You know, it'd be most efficient at noon, perhaps, but not so much in the evening. You know, well, there's a bit of that with some of the wave energy converters as well. Some wave energy converters are tuned for particular wave characteristics as well, and their design, it has to be chosen. They'll be tailored for a particular location. We also looked at the extreme waves that we could expect in 20, 50, 100 years. And to do that, we just use a standard method, which is to fit the You use a potential over threshold method to identify peaks in your model time series, and then you fit that to a Weibull probability density function, and then the tail, you can use that to estimate the extreme waves that you might expect going forward. And for the offshore location here in 100 meters depth, you see that we might expect waves of nearly 17 meters significant wave height every 100 years. And that means that some waves will be twice that big. We know that in the past we've had giant waves because the lighthouse I showed you at the beginning, that has been inundated with waves going up 40 meters up the side of it, you know, the swash. So this is the experience of the lighthouse keepers in the past. And once your wave energy converter is in the sea, you need to know what opportunities you have to deploy, recover, service, send submersibles down, and so on. So what weather windows do you have? So we just organize the data in windows. The columns are the months of the year. Each table is for a different wave height, and then the numbers are the number of half-hour periods on average that you can expect with those conditions. And one of the conclusions we come to is that you do find significant weather windows in the wintertime as well as the summertime. That's very important, because if a wave energy converter goes down and needs to be serviced, you know, you're losing money, and it's important that you can quickly go and fix it. That goes into the cost calculations. So Westwave is the first commercial wave farm being developed in Ireland by ESB. And here we just see the development of the project announced this year. We're one of the commercial partners in that. Implicit in the project will be a competition between wave energy converters to see which ones to use. It's not decided at the moment. We don't know which wave energy converters are going to work or not, to be frank. There's a lot of secrecy around their development. You can't find out how well they perform or their efficiency or their cost. So that decision is put off until 2014 perhaps, 2013, to decide. Also, the location that the wave farm is going to be put in has been narrowed down but not yet decided. But at any rate, the intention is to have the wave farm operating in 2015. The project was set up by ESB, which is publicly owned, so it's conceived as an opportunity to develop the supply chain for a wave energy industry. And they've applied for EU funding, as well as putting their own money in. It's seen as public good. I think ESB recognise the risks, and they don't anticipate they're going to make a lot of money out of this. At the bottom here you see some pictures of the technologies that are being considered for their first wave farm. On the left you see Oyster, which is a Northern Irish and Scottish company called Aquamarine developed that. And it's like, I don't know if you're familiar with it, but it's a shoreline device, and it's underwater, it's on the seabed, and it kind of moves like that as the waves come past it. And directionality is very important for it. There you see Wavebob, which is an Irish company, and it uses the differential motion deep in the sea compared to the surface waves. It uses that differential motion to pump oil and to drive turbines for electricity. Or I should say that Aquamarine's device pumps water, which is brought back on shore. The pressurized water is used to convert it to electricity on the shore. Here you see something called Ocean Energy, which is again an Irish device developed in Cork, and it has a hull, a strange hull, which has got tunnels in it, and the waves compress air through those tunnels up through a channel which drives a turbine that's used to generate electricity. So it's a complicated device, and there you can see the actual turbine just here that the compressed air is forced through. And here you see, you're probably familiar with Palamis, the sea snake, because I know they've got some around in Aquadura in Portugal. Do you know them? And here you see just the list of project partners, and it just shows you the diversity, the ecosystem of people that will help to develop the first wave farm. And here you see insignificantly us, Numerics Warehouse, but also apart from the technology providers, the wave energy companies, you see Vattenfall, which is one of the largest energy utilities in Europe, Swedish utility. Ton Energy, that's an Irish company, quite like our company, Numerics Warehouse, but they're more involved in choosing locations for wave farms. Arup, the consulting engineers, HMRC and CMRC there, down in Cork, the Marine Institute of Ireland, county councils. Alstom are a company involved in modelling grid power, and you know they're grid specialists. Siemens, TechWorks are involved in an Irish company involved in making measurements at sea, and Harland and Wolff are there. You see there, Harland and Wolff. They're the shipbuilders in Northern Ireland, in Belfast, that made the Titanic. Solicitors, you know, very varied group of companies come together for this project. Where to put it? Well, I think one of the things that I want to get across to you is just how low important the wave resource is, about where you put a wave farm. I already mentioned about the grid and problems there. Here are some of the other considerations that you must look at. You have other marine users. So the sector size shows you the importance, if you like. The wave power is only, 30, 40 degrees of the 360 degrees. Marine traffic, aquaculture sites, tourism, the ability to bring electric cables on shore past cliffs and things like that. Availability of a port, using those weather windows, how quickly can you get out to a wave site to service it? Other marine users, fishermen, and so on. And then locations of special areas of conservation, protected areas, marine protected areas. You want to avoid those as much as possible. And Westwave decided, out of all the sites that might be available, you see and the top one is the site that I've been modelling. That's one candidate, another candidate just south of that in Achill Island, and then the third candidate in the south in County Clare, which has a much lower wave energy resource, but very good grid connections, and is probably the location that they're actually going to pick. And also there's very few special areas of conservation and so on there. So the company Ton Energy did this study. It was a big study, and they assigned weightings to each of these different categories, and they came to the conclusion with recommendations of the best site. I won't go through all this. These are just a list of some of the issues that are chosen to suggest the initial development zones that the government's recommending. So, I've already mentioned wave modelling. And I chose in this talk not to concentrate on numerical modelling as such, but I'll talk to you in general about where we're going with the modelling. The main use of the modelling is to reduce the risk for wave energy developers. By predicting how much power they can produce is the obvious one, and its intermittency. But also, what can we do to help them choose locations where the seabed isn't going to change too much, the sediments aren't going to move around too much? What forces are going to be exerted on the underwater structures of wave energy converters, the peak loads, the effect of all the currents and on the underwater structures, the impact forces of waves, and how that will affect the performance of wave energy converters, how much wave energy will be extracted from the wave climate by farms of wave energy converters and how that will impact the environment. And to do that, what you really need is you need coupled models. You need to, having just a wave model isn't enough. The wave model has to run at the same time as a hydrodynamic model. And to get the best results, you really want to couple that to a weather model as well. And then, to add to all of that, you can add your sediment dynamics models, okay? And if they all run at the same time, then it's beneficial for each of those models. For instance, if SWAN and ROMS are coupled, the wave and the hydrodynamic model, then SWAN, the waves are sitting on top of currents, which will affect the spectra. The waves break and create turbulence that mixes the upper layer of the ocean, that changes the current structure. Also, the wave orbital velocity is added to the three-dimensional currents in the model to affect the resuspension of sediments at the seabed. The sediment is moved around on the seabed and changes the shape of the seabed that affects the currents for shallow water applications. If you've coupled it to an atmospheric model, then you've improved your momentum and heat fluxes. So where are we? Well, we have a model, a coupled weather, wave, and hydrodynamic model that runs for a Bell mullet. And I don't have any data to show you here. It's quite recent, in the last month, that we have this model running. We're just in the process of adding sediment dynamics to that, which is one of the really big prizes of doing this, because that's one of the big problems is if they put a mooring down somewhere, is the sediment going to move? You know, is it going to get buried? And you know, if you've got more than just a mooring on the seabed, if you've also got a transformer, for instance, then is that going to get buried too? You know. So this is what we're concentrating on now, is the sediment dynamics problems. But to do that, you need to couple it to the hydrodynamics, the waves, and so on. And here you just see a sediment map for the area, the 30 kilometre by 20 kilometre box, showing this sediment map was produced by post-processing swath multi-beam bathymetry data, mainly, to actually look at the strength of the acoustic signal that's reflected from the seabed and the nature of the pulse that's returned, using Questa tangent software to categorize the seabed, and supplemented that with some very old UK Admiralty measurements and also sediment samples that have been taken in the process of various cruises over the last few years. So it's quite hard to end up with a sediment map like this. You can see how rocky it is, the purple areas. You see the sandy areas, and you can see the location where the green dots are where sediment samples have been taken, but that's really where the wave energy converters are going to be placed. So what I want to answer is how variable is the seabed in that location, in those locations. But what else can we do? What else can we do? Well, here I show some results of a study that was conducted by Vengapal and Smith for EMEC in the Orkney Islands, where they used Mike 21 wave model to extract energy from the wave climate and see how that affected the general wave climate. On the left-hand picture you see just, I think they've got boundary problems there perhaps, it looks to me like, but you can see the progression, the reduction in the significant wave height as you approach the shore. If you put in some wave farms here, and you can just see them just up here, but they extract some of the energy. They're kind of porous, and I don't know what methodology they use to extract wave energy, whether it's arbitrary or whether they have information from the wave energy converters to do that. But you can see, certainly, you can see the effect it has on the wave energy arriving on the shore. Now that might have a big problem sediment dynamics for the, what happens to a beach, a tourist beach maybe, in that locality. So we're looking at how to adapt wave models to do this as well. And I'd be interested in discussing this with anyone that's interested here in doing that, for instance. I think it'd be a valuable thing to do, because once you've done that, you can insert wave energy converters, and you can actually see how they relate to each other and how they affect the amount of wave energy for each of them. You can design efficiently your wave farm, but also you can look at the effect on the environment. So I'll stop there, but I'm very happy to talk about any of the modelling aspects either now or afterwards if you wish. And thank you very much.